Next, we're going to take a look at inverse trigonometric functions. So let's put the topic title up. So inverse trig functions. Now, basically, we're going to be combining what we know about inverse functions with the three main trigonometric functions: sine, cosine, and tangent. Now, right away, you should have some questions in your mind, because if you recall the basic graphs of sine, cosine, and tangent, which I'll draw right now. So sine, remember, starts at 0, it comes up, and then it goes down over one period. So the period is 2 pi. So the half period is pi. So sine looks like this. But then it repeats. Right? So then it goes like this, and it goes like that. And then it keeps repeating every time we pass an interval of 2 pi. So it just repeats on and on and on. Similarly, cosine does the same thing, except instead of starting at 0, it starts at 1. So it starts at the peak, and then comes down, and then returns to the peak in 2 pi. And then it repeats that pattern every 2 pi units. So there's 4 pi, and so forth. So right away you should be asking, well, how can we compute the inverse function for a sine or a cosine? Because in order for a function to be invertible, it has to satisfy the horizontal line test. That is, for every output, for every y value, there has to be a unique x value associated with that. So for example, if I said, here's a y value, and it has to be between -1 and +1, because the range of the function is between -1 and +1. And if I were, so let's say this is just some y value. So the question is, well, cosine of x equals to y. So y is given. It's, whatever number's right there, maybe 0.6, 0.7, something like that. Find the x value that corresponds to it. Well, we can draw a horizontal line, and we see that there are many x values, each which give the same y value as the output. So all of these points, this point, this point, this point, this point, and so forth, all of those x values produce the exact same output. So the function cannot be invertible in the traditional sense. In other words, given the y value, there is not a unique x value that took you there. You can't trace back uniquely to where you came from. So we need to figure out a workaround, because oftentimes you'll have trigonometric functions and you will want to solve equations like this. And there is an inverse trig function, so to speak, that we actually use and we can use to solve problems. For example, if you think back to that Ferris wheel problem where you're riding a Ferris wheel and your height is given as a function of time, you might ask the question, well, at what time did I pass through such and such height? Or if you have tides in the Monterey Bay, the tides go up and they go down, and it varies as a sinusoidal function. Okay, well, at what time is the tide level at this height? Maybe your boat, in order to navigate your boat through a river, the tide has to be at a certain height. So what's the earliest time you could actually leave the boat dock and actually sail out into the sea, given the fact that the height of the water level has to be at some minimum height for your boat to be able to actually navigate? So questions like this. So there are lots of practical situations where we might want to solve an equation like that, and we can do it. So the solution turns out to be doing something called restricting the domain. So we'll basically be restricting the domain of these sine and cosine functions in order to create a mini function, a function within inside of the function that is invertible. So with the restricted domain, the function does become invertible. So to see this, let's start with cosine of x. So let's draw the y-axis, and let's call this theta. So let's call this y. We have +1, and then we have -1. And then cosine starts up there, and it comes down, and it goes up like that. And then it repeats. So there's 2 pi, pi. And then on the other side, it of course continues in the similar. So we're at negative pi somewhere over here. So this is y is equal to cosine of theta. And it's important that when we use trigonometric functions, sine, cosine, tangent, always be in radian mode. So in pre-calculus mathematics, oftentimes, you have a degree mode on your calculator, and you're given, basic trig examples, angle 57 degrees, plug it into the sine and cosine function. But in calculus, we always want to use radian mode. And the reason is that the derivative rules that we'll learn later in chapter 3, which is based on the theory of chapter 2, all of calculus kind of, it works out much simpler with these functions operating in radian mode. So we'll see why this is true later and why it's necessary to keep these in radian mode. But for now, let's just get in the habit of always, when we see a sine function or a cosine function, it should automatically be considered to be in radian mode. And always make sure your calculator is set to radians. So on graphing calculators, you can go into your settings and set that. For a more traditional calculator like this is the TI-36X Solar. Every time I turn it on, I have to do a switch to radian mode. But that's automatic for me. So make sure to always be in radian mode. Well, this function, as we mentioned earlier, is not really invertible, because if you look at a y value, think about a horizontal line, many x values give an output that's equal to that one y value. So what the idea is, we restrict the domain, and for the sine function, we instead think of the domain as restricted from 0 to pi. So we think of sine of theta for theta on 0 to pi. So for theta on 0 to pi, we just get this one arc, right? So that is what the sine function looks like when it's restricted to that interval from 0 to pi. Now you'll note that for every y value in the range, in other words, for every y value between -1 and +1, there's a corresponding theta value somewhere between 0 and pi. So notice that this sweeps out at -1 at pi, +1 at 0. It traces out every point in the range. So the range maps uniquely to a single theta value between 0 and pi. And this is exactly what the inverse cosine function is defined to be. It's and I did write sine down here, didn't I? Cosine, if you were worried about that, that's a good catch. Cosine of theta for theta on 0 to pi. So that's exactly how the inverse function, so the inverse cosine function, so it's also called arc cosine of theta, or cosine -1 of theta, like this. So this is kind of the common notation. Now, since this is the first time we're encountering this inverse cosine notation, or inverse trigonometric functions in general, there's a very important warning at this point that I'd like to bring to your attention. If we write cosine squared theta or cosine cubed theta, this is a shorthand for the function cosine of theta squared, cosine of theta cubed. So it's the output raised to the second power, or the output raised to the third power. However, cosine to the -1 theta is not cosine of theta to the -1. So that's not equal to cosine of theta to the -1, or 1 over cosine of theta. So these are the same thing. Oops, what happened? So these two are the same, right? Because when you raise something to the -1 power, you're taking the reciprocal. So cosine -1 theta is not the reciprocal of cosine of theta. This is reserved specifically for the inverse function. So when you see the -1 up here, think of it like f inverse of x. So we had f of x and f inverse of x are inverse functions. So specifically when you see -1 for the exponent on a sine or a cosine or a tangent, it always refers to the inverse function, not raising the output to the power of minus 1. Right? So we give a different name for the power of minus 1. So that's why 1 over cosine is called secant theta. So secant theta is a special function just to denote the reciprocal of sine. So instead of using those negative 1 to denote 1 over cosine, the negative 1 is reserved for the inverse function, not the reciprocal. So it's a little bit of confusion there, it's a little confusing, but that's the convention, that's what was adopted. So you just have to kind of get used to that and be aware of that pitfall. When you see cosine to the minus 1, it's not 1 over cosine. 1 over cosine is secant theta. Cosine to the minus 1 is called arc cosine. So this one's arc cosine theta. You can also say arc cosine. So arc cosine theta is specifically designed to be the inverse function not of cosine theta, but of the function cosine theta defined between 0 and pi. And note that this is different than just saying cosine of theta. Because since when you say cosine of theta, it's all, if you don't specify a domain, it's always implied that you have the largest domain possible. Cosine of theta is defined on the entire real number line. So cosine of theta will have a value, an output assigned for every real number input. So that as a function is different than this function, which is only defined for the interval from 0 to pi. So this is called the restricted function, or the function on the restricted domain. Don't have to worry too much about that terminology, but that's what that means if you hear it. So cosine of theta, defined on the domain 0 to pi, that's the restricted domain, just for basically 1/2 period of the cosine function. That is a function that is invertible because this function, this red function right here, the graph of this function, does satisfy the horizontal line test. So therefore you have an inverse function, and that inverse function is the arc cosine function. And that arc cosine function is, when you do the arc cosine on your calculator, this is what it gives you. It gives you the return, so it basically solves, cosine of x is equal to y. So if you give it a y, it solves for x, but it finds the value of x specifically on the interval from 0 to pi. So you have to be careful when you hit arc cosine on your calculator or arc sine, it's only giving you the inverse value on a particular interval. So for arc cosine, it's giving you a number between 0 and pi. That might not be the solution to this equation you're looking for. So if you're trying to solve, for example, cosine of x is equal to 0.5, you might, based on your real-world application, you might want to find it when the tide's going up instead of going down. But on this segment, the tide's going down, so you might actually be looking for the solution over there. So I'll talk about how to deal with finding other solutions to this equation in a moment. But first, let's introduce arc sine and arc tangent. So we said that cosine inverse returns a value on 0 to pi. Sine inverse will return a value on minus pi over 2 to pi over 2, and then tan inverse also minus pi over 2, pi over 2. Of course, by inverse, I mean the inverse function. And actually, let's make these round, because tangent is not defined at pi over 2 or minus pi over 2. So to see why this is true, let's take a look at the graph. So sine looks like this. So there's pi, 2 pi, minus pi, minus 2 pi. So we can't go from 0 to pi because sine functions, so this is y is equal to sine of theta. The sine function is not invertible on the interval from 0 to pi because for any output you have 2 inputs that lead you there. So instead we go from minus pi over 2 to plus pi over 2. And on this segment, we just get this curve right there. It looks similar to that restricted cosine function. So when we use the arc sine function, we're going to receive a result that's between minus pi over 2 and plus pi over 2. Similarly, if we think about the tangent function, tangent has these vertical asymptotes. So this is at pi over 2 with a negative, pi over 2, 3 pi over 2, minus 3 pi over 2, and it repeats like that. So it has these vertical asymptotes here. And as you might have suspected, we're going to take just the section of the tangent function that goes from minus pi over 2 to pi over 2. Now you notice the tangent of x hits on every single y value on the as x varies from minus pi over 2 to pi over 2. So therefore the domain of the arctangent function is actually all real numbers. So this is really kind of like the range of the arc cosine, arc sine, and arctangent. The domains of those inverse trig functions minus 1 to 1, minus 1 to 1, because remember, cosine of x and sine of x have a range that goes from minus 1 to 1. So when you do the inverse function, the domain of the inverse function will be minus 1 to 1. For the arctangent, since the range of the arctangent is all real numbers, the domain of since the range of tangent is all real numbers, so here's y is equal to tangent of x, and the range we get all real numbers as outputs. So the domain of the arctangent will be minus infinity to infinity. So any number from minus infinity, maybe this number way up here, this number has a unique x value such that tangent of x returns that number. So there's this one-to-one correspondence between any real number and the numbers on minus pi over 2 to pi over 2. So this is the outputs for the inverse trig functions, and then these are the possible inputs. Now, if you're looking for a solution to a trigonometric equation, and the solution you're looking for is not one of the actual value that you get out by these inverse functions, you kind of have to think about the symmetry of the sine and cosine functions and what the graphs look like in order to figure out what the appropriate solution is that you're looking for. And let's do an example of this next. So let's say that we want to solve 0.3 is equal to, let's make it sine. Cosine's okay. Yeah, why not? Cosine of 4x. So solve for all x values on, let's make it 4 pi x. We'll see what happens on the interval from 0 to 2. Okay, so we have to, let's do something a little bit, let me just say cosine of x. Let's just say cosine of, let's call it theta. Solve for all theta values. Let's just keep it simple without anything. And then let's go from 0, let's do this. Let's go pi to 2 pi. Right, so first of all, let's draw a picture. Cosine of theta, it looks like this. There's 2 pi, here's pi. So 2 pi is actually like right here at the peak. And that should be really at the peak right here. Okay, so we're looking for what value of theta between pi and 2 pi satisfies the equation cosine of theta is equal to 0.3. Well, using the arc cosine function, what we can get is we can get the value, so let's drop 0.3 like this. We can get the value of theta between 0 and pi that tells us cosine of that value of theta is equal to 0.3. So here's 0.3, and the inverse function gives us something like this. So all I have to do is switch to radian mode, 0.3 arc cosine, And my graphing calculator tells me that arc cosine of 0.3 is approximately 1.266103673. So that's not the value I'm looking for, because I'm looking for a value of theta such that cosine of theta is equal to 0.3, such that that value of theta lies between pi and 2 pi. So this has given me this value of theta right here, whereas I wanted to give me the value of theta up here. So to understand how we can get the other value, let me draw a larger, bit more careful drawing. There's 2 pi, pi, here's pi over 2, and 3 pi over 2. So pi over 2 is about 1.6. So this value, as we would expect, hit before pi over 2. And then we want to find actually the one over here. Now, the trick to doing this is to look at the symmetry. So you'll notice that if I draw a line at theta is equal to pi, I've basically created a mirror. So the function looks exactly the same on both sides of that mirror. So they both agree at the mirror point, and then as I move a little way this way, I move a little way that way. So if I move over so much in x to the left versus so much x to the right, the same thing's happening to the y value. So I can use that symmetry to figure out what this solution is. So it's a symmetric about pi, so let's figure out for the root that we know, so this is at 1.266, it's that much less than pi, so this root must be the same amount greater than pi. So in other words, if we do pi minus 1.266, we get this length here. We'll call that L. So L is equal to pi minus 1.266. Now this length is also L, so our second root, so our theta value, is going to be pi plus L. Well, pi plus L is going to be pi plus pi minus 1.266, so that's 2 pi minus 1.266 dot dot dot. So normally I don't write that all down. You can just kind of look at the picture. So 0.3 arc sine, we have our 1.266 number. Let me just subtract that from pi, and that's L. L is 1.875, so I have that in my calculator, 1.875. And now I just want to add that L onto pi. So instead of subtracting it to get to this root, I'm going to add it to get to that root. So I add that to pi, and I get a theta value of 5.017081634. Now you'll note if I did 2 pi minus 1.266103673, I would have gotten the same result. But I just kind of did that as part of my, just said, how far is this point to pi? Let's take that distance and add it to pi instead of subtracting it. So instead of going, this way to get to that point, I'm going this way to get to this point. And now we can always check our answers. So that's the theta value. Now let's just hit the cosine function on it. And what do you know? 0.3. That appears to be backwards, but it's 0.3. That's the value of theta that we're looking for on our given domain. So in a similar fashion, you can find other values, other roots. You just have to really know what the graphs look like, draw the graph carefully, and then use these sorts of symmetry to say, oh, the same thing's happening left and right of this line. So if I'm going up this way and this way, if I'm this much less than pi, I should be this much greater than pi. So I don't want to give any hard cut rules. Just look at the picture, draw the picture, make a diagram, and look to see yourself what's going on. And always confirm your answer, check it to see if you are correct. So that's how you solve problems using inverse trig functions.